Hi, everybody. My name is Louis Ahmed, and thanks for joining this talk. I'm looking forward to the discussion session later. I'm going to have to go somewhat quickly over some of the theoretical or experimental details of what I'm about to talk about. So please feel free in the discussion to raise these questions, and I really look forward to the discussion. All right, so the topic for today is optomechanics for ultralight dark matter detection. And specifically, we're going to talk about some of the limitations and opportunities in optomechanics for detecting forces from ultralight dark matter. Now, in my view, optomechanics is one of the slightly understudied fields of quantum sensors. And that's because historically, I believe, a lot of the proposals have been centered around pendulums, essentially, so mirrors on strings, which are then driven by a laser, and the light bouncing off of the laser gives information about the position of that sensor. And I'm now actually going to be talking about a slightly novel version of this, where we still have a detector, which I'm going to draw here. I'm going to draw a little sensor, and I'm going to draw this optical field that is around it. And as you can see, is very generic for now. But the point is that this is then going to create, this optical field is going to be shaped with lenses and different versions of the setup, such that you have a potential on the sensor that is a harmonic oscillator. So this is a simple harmonic oscillator. And harmonic oscillators have equations of motion that are very well known, very easy to understand, and have a noise spectrum that is at the quantum level quite is somewhat related universally to other quantum sensors, but that we will study a little bit more here so that we can actually optimize these detectors for forces, oscillating forces on these sensors, because as harmonic oscillators, they should have a resonant motion, or they should have a resonant peak of their power spectrum and their sensitivity around that point. So the equation of motion of such an object is very simply x dot dot plus gamma, so the damping rate, times velocity, and plus x squared, kx squared, sorry, that's k, that's the spring constant. And then you have, so there's some damping involved now in the system. And then there is this, and then there's a force driving it. And then of course, here's this is in units of force over mass, like this. Now, this force might actually be forces from dark matter fields, dm I'll call, or maybe a noise. So there could also be, right, this could also be noises. And these noises naturally occur in such systems because the light bouncing off is this way, is being observed and is giving information about where the sensor is, and therefore what forces are being applied to the sensor. Okay, this is my observer. And these there is noise intrinsically in the measurement process, as is well known, for example, from our intuition about the uncertainty principle. And indeed, when one calculates the power spectrum, so essentially like take the Fourier transform of the above, and then look at the power spectrum like this. So this is it's called SXX. And then on the other side of this equation, if you do the same thing, the power spectrum is going to give you SFF, so the power spectrum of the forces. And what we want to know is what is the sensitivity to forces, because we want to know in what case does this FDM, when this FDM is larger than Fn, we and more specifically, when the power spectrum of SSTM is larger than the noise, we want to detect that. So, and it turns out that from a derivation that I don't have time to go into detail about, but I can give you the intuition for the result. SFF of the noise has two components. It is what is called a back action and a shot noise. Shot noise. Now, this is, so going back to the picture of the light scattering and measuring the position of the oscillator, the shot noise is going to be, it comes from the statistics, or the limited statistics that one has when the observer is seeing individual photons that have scattered off of the sensor and is being observed now. Whereas the back action is due to the excitation that those photons are inducing in the mechanical motion of the sensor when it is making the measurement. And so this is really analogous to the, completely analogous to the uncertainty principle. And in fact, the product of these two is, the square root of the product of these two is simply h bar over 2. Now, to calculate, now the expressions for SVA and SN are quite simple. I'll show them here. So it is equal to, now first of all, I'm going to assume that the two are equal, and that is because we are going to assume we are at what is called SQL, or the standard quantum limit of these sensors. And in that case, SBA is equal to SN. And so now we can just calculate one of them. And so SBA, for example, I know the expression for this is very simple. It's just proportional to the, it goes proportional to the power of the laser. So it's power, so it's literally just 2/5 times laser power, laser frequency times laser power. Technically, it's the scattered power on the, well, here we can assume a small sized beam, for example, where a beam is the same size as the object. Now, this scattered power is now going to be, so the more power, the bigger this is. And SN actually, for more power, is going to go down. And so that is why actually there is there's actually a power such that this is the minimum. So there's a sort of PL, actually I'll draw it like this. There's a PL SQL, really. But I won't write it. I will avoid writing SQL on it every time I write it down. Okay, so this now this power is well known because it is also the power that is required to create the harmonic oscillator in the first place. And so actually I can write this as I can write it as 1/10 omega L M omega squared Z0, where Z0 is the distance from here, the focus of the laser, because this laser is actually being emitted away from this focus and is therefore becoming defocused as you go away from it. So this is the distance Z0. And then the frequency of the trap is omega squared. M is the mass of the particle. And again, omega L is the frequency of the laser. So really, this is a quite simple expression. And now all I want to do is essentially to minimize this quantity. Now, Z0 is, now of course, most of these things are going to be fixed. This is fixed. This is difficult to change, but you can ask me about it later. And this has a minimum. It has to be larger than the wavelength of the light, or the inverse of the frequency. So really Z0 frequency are actually going to be related. And in fact, this may be in which case you can usually simplify it in a bit further to just M omega squared. So really, the only change you can do is mass. But historically, especially in the experimental community, it has been assumed then that going for smaller mass objects was a good idea. But actually, what happens is that when objects are very small, smaller than the wavelength of the light, they are what are called Rayleigh scatterers, where the wavelength of the light is smaller than the size of the object, and the object scatters, that becomes an electric dipole, which coherently scatters the light in the object, and therefore the entire and therefore the noise SBA actually changes, is no longer the same expression, and ends up being something that goes as mass squared. And that's no good. Why? Because when we're trying to detect dark matter, we're going to do the following. We're going to take the ratio of the, as I said earlier, if we're going to take the ratio of the SDM over the SN, and you typically actually would take the square root of that. And then what we do then, and because SDM is going to go as mass squared, always, for example, for coupling of dark matter, scalar dark matter to quark masses or to CT scalar electron masses, or for a vector dark matter coupling to B minus cell charges or BUB charges. That's the case. And it goes as, in fact, it goes as M squared rho dark matter. So the point is that we then need to, we want to avoid this regime of the particle being too small. And we want to instead be in this regime where the noise goes as M only, because then the SNR, so this was what I showed here was the SNR. We want the SNR to be as big as possible, of course. So that means that with a large mass, actually, I can get to, I can now, in this regime here, I can actually get a really good SNR. So that's what we're going to do now. And we're going to take specifically, we're going to take a mass of about 0.1 grams. And this is going to lead us to the following bounds, which I'm going to draw here qualitatively. So we're going to see that, so typically for example, a G that is a B minus L charged dark vector coupling, we're going to have microscope and wash type experiments. Please ask me more in the discussion why those are going to be so helpful. So I'm going to sort of draw them up here. This is going to be around 10 to the minus 23-ish. Although actually microscope is going to go a little further than 10 to the minus 25. And then we actually have calculated, and this is around a kilohertz. So 10 to the 3, and this is omega. And we find the following. We find bounds that go about like this, across just above above a kilohertz. And here we are talking around 10 hertz. And what happens below 10 hertz, unfortunately, is that seismic noise becomes very important, and we haven't studied the mitigation of it, but we will. But for now, we're going to assume that we're basically going to cut off here. I mean, there's a bit of a power law really for it, but yeah. But so this is actually our sensitivity here, and we find that is better. And of course, we're going to release a paper soon that's going to show that. And I think here we are reaching about. Let's see, at a so we were reaching about 10 to the minus 26 approximately. So we're several orders of magnitude more sensitive. And this is great news. And we expect once we start looking at other couplings, so GB, G to where it's mass of electron, et cetera, that we're going to continue getting new bounds. What we don't have, there are still some, and so there are a few more insights, I think, that can be gleaned from this. The first is that we have a good effect, a very strong effect from scaling the size of the particle. That is and in fact, we could even scale it a little bit more if we instead were at not 0.1 grams, but instead we were at, oh, sorry, this was 0.1 milligrams. Sorry, it's 0.1 milligrams, and those were the results for 0.1 milligrams I just showed you. If instead of 0.1 milligrams, we were at 0.1 gram, which is possible, but requires, so at this point, we also need to, I should maybe briefly mention that there's also an optical field from below that is supporting the particle, is levitating the particle, because there is the pull of gravity, of course, in a real world experiment. And we are limited eventually at large masses by the amount of power that is required to levitate the mass, so mg, or the force, I mean, to push against the force of that mass, that is mg. And at about 0.1 grams, maybe a gram, optimistically, is where you get to laser powers that reach those of, say, LIGO and other large experiments. But 0.1 milligram, that can be done in the lab tomorrow. Now, that is the other. I should mention also that this is, although what we used here was an extremely generic experiment, this actually there's a very concrete setup actually that that I can discuss in just give it a couple more details about here for those who are interested. So this specifically is because it is I should emphasize, this is a new proposed setup that has not been done by the optomechanics community, but through collaboration with optomechanical experimentalists who are specialized in looking for dark matter. We have conceived of we've conceived of a novel experiment that will be much more powerful towards detecting dark matter. And in this case, what we do is we've scaled up the mass, and this seemed difficult in the past in the optomechanics community, especially because there was no Rayleigh scattering that would levitate the particle, as is typical in that case. And so instead, what we have to do is we have to take a beam from below, which has been done in the past in other contexts. And then we have to take horizontal beams. So we have these beams that come in from the sides, either side, and that are then focused out such that the further you are away, the smaller the force, because this object is just a mirror essentially. And the closer it becomes to either mirror, the more it is pushed back to the center, effectively creating the harmonic oscillator we needed. And in fact, we can, to change the frequency, we have now 2 degrees of freedom. We have the degree of freedom of the intensity, of course, to do this, but we have also the degree of freedom of the distance of the object to the lenses, and this allows us to actually replace. This is why you do not see the laser power anymore in the noise here in this expression, and is instead replaced by the distance, because actually we end up writing one as a function of the other. All right, so this is actually, and I should now maybe briefly mention the bounds from our competitors, which are actually, for this, is actually up here about a couple orders of magnitude. It's like this. So this is what has been done previously with Rayleigh scatterers, for example. As I said, I look forward to the discussion. I should say also that other couplings are going to be studied by us very soon with this setup. In particular, there is also a angular stability in the system built in, and therefore torque actually could also be torque in inducing dark matter effects, such as those from pseudoscalars, could also be detected. And so I hope I've convinced you that optomechanics, novel optomechanical setups are worth exploring and can lead to some very strong and yet realistic and easy to do in the near future, I should emphasize, experiments that can give new bounds on ultralight dark matter. I thank you for your time, and again, I look forward to discussing in the session. Thank you.